Today we have something different for the audience of Theories of Everything, and I'm super excited to speak about it. I'm going to get into exactly why today's episode is different, but I'll ask this preliminary question, and perhaps in your answer it'll be clear which direction we're going. But what are primordial black holes, and why should anyone care?
Good. Okay. So primordial black holes are as yet hypothetical. We don't know they exist, but they're a really intriguing idea. And they were put forward by a few different researchers more than half a century ago. So the idea has a long history by now. The idea in brief, and I'm sure we can unpack it together soon, is that these are black holes that would have formed not through the ordinary route by having a star that exhausts its nuclear fuel, gravity wins, it collapses and crushes down, and forms what we now call an astrophysical or stellar collapse black hole. And we now know those are real, and they litter the universe. They're very common, in fact, these stellar collapse or astrophysical black holes. These primordial black holes are hypothesized to follow a different route, that they would actually short-circuit all of stellar evolution, and they would form by the direct collapse of some original early universe or primordial lumpiness, some inhomogeneity in the distribution of matter and energy, which is different from saying you had a star and it had a whole life cycle and collapse. So these things could form not only independent of stars, but long, long before there existed stars. In fact, before there existed stable atoms. So these really have a very, very different history if they exist in our cosmos. And so we can unpack that and talk about it some more, but one among many reasons why they're now of interest to a growing number of researchers across sort of fundamental physics and astronomy and cosmology is because these might be a candidate, for example, for dark matter, if they have certain masses and properties. We can talk about that. If they form with larger masses, then they might be candidates that could explain these supermassive black holes that we now know lurk within pretty much every galaxy that's been seen. So we have lots of questions about the cosmos, and primordial black holes seem to offer a pretty cool way to maybe start to answer some of those really long-standing mysteries.
Broadly speaking, there are these two ways of learning large swaths of material and connecting them together. So one is to learn everything, like the everything that's in the term Theory of Everything or this channel's name. However, it's difficult to do so in a manner that's more than, say, 3 or 4 layers deep on any given subject, just due to time constraints. Now, the next method is to paradoxically specialize in one tiny domain and then do that extremely well. And this sounds counter to the whole spirit of the wide scope of everything. But to learn that one specific topic, you have to then approach it from multiple angles. I don't know if you've played this game Katamari, or if you've heard of it.
I don't know it, no.
Okay, so in Katamari, you're this tiny little figure that then pushes one special object. It's small. There's a stickiness to it. So you start to get some small bits of paper attached to it, maybe some toothpicks, and then eventually a glass bottle, and then eventually cows and buildings. So when I talked to you, initially we were going to speak about the history of physics, and we still will touch on that later on in this conversation.
Yeah.
But speaking off air, it was clear that you used primordial black holes as this sort of subject that touches every other area related to fundamental physics. And I don't think you intended it to be as such. So I want this episode to not only be an exploration of primordial black holes, and not only every other area of fundamental physics or as much as we can touch, but also this generic process of having a topic that allows one to become both a jack of all trades and a master of some.
Yes. I think that's a really great way of putting it, Curt, and I agree. And that's an unintentional journey I now find myself on. I didn't plan that when I began working in a more focused way on primordial black holes 3-4 years ago with some amazing colleagues and students, collaborators. But I think you're right. Now in hindsight, looking at the path I myself have really enjoyed wandering in research the last few years, following the primordial black holes, following the idea of primordial black holes really has led me to not every area of physics, of course, but to a bunch that were familiar to me. I could start from a kind of familiar home base. That's how I began first thinking about these. We can talk about that. But then really to other areas of physics that I knew a little about and some that I knew very, very little about. And now I've had the great luck to spend some time and learn more about those other areas as well. Always, as you say, connected to how might these relate to primordial black holes as my central question. And then I don't know if the spokes radiate inward or outward, but around that becomes a node around which I, and again, many very wonderful colleagues, can try to connect lots of dots among areas of physics, among subfields, among topics that, often are treated kind of as if their own separate lanes. So it's been a great joyride. It's been really actually very fun for me to do, I think, very much like what you're saying.
Tell me more about this familiar starting point of yours.
Yeah,
Why don't you just walk us through your journey in physics? Or even your just academic journey in general. Maybe it didn't start with physics.
Sure. No, I'd be glad to. So we can turn the clock way back. As a high school student, like maybe many people today who enjoy this channel, I was really, really hooked on what you might call kind of popular science. And at that point, it was mostly books, not amazing multimedia stuff. Cheap paperbacks. I was growing up in the era when Stephen Hawking's book, A Brief History of Time, first came out. So I was still in high school when that book appeared in the late 1980s, for example. But even before then, I was reading just a slew of, I think, really good, really high-quality books, written for non-specialists, for broad readerships, written often by practicing scientists, some by very talented science writers, and some people who were really kind of combining the two. And it was just, thrilling. It was just felt like an intellectual adventure in my, teenage years, my high school years. Mm-hmm. And some of them, I remember some very dearly by the author John Gribben. And so he had a whole series called In Search of Blank, In Search of the Big Bang, In Search of Schrodinger's Cat, and he had many that would eventually fill the shelf. Those two that I mentioned, the Big Bang and Schrodinger's Cat ones, really grabbed me, and they came out even before Stephen Hawking's, much better known book. And the first of those, the one on the Big Bang, was really a tour without very much mathematics, probably none at all, but a tour of the big ideas that came together to what we would now recognize as the Big Bang model. And he closes the book with some early hints about cosmic inflation and a kind of revised understanding of what we might now call the Big Bang. The book came out just a few years after the first proposals by the real experts on cosmic inflation had been published, as I later came to realize. These books were published in the mid-1980s, and the kind of foundational papers on cosmic inflation were published in 1981, 82, 83. This was hot stuff by the time it had already made it into these popular books. Likewise, for Gribben's book on Schrodinger's cat, of course, as the title suggests, it was a really, I thought, engaging, inviting introduction to quantum theory. Some of the juicy, nuggets that many of us still stay up late at night thinking about. Things like what we might call the measurement problem, the role of superposition of coarse quantum entanglement, and so on, Bell's theorem. And again, I just was hooked. Okay, so I get to my undergraduate studies, thoroughly convinced in my soul I want to do physics. That turned out to remain to be true. But really curious also about these kind of human stories. Who were these people who stayed up late at night wondering about these things and often having very extended arguments and debates? And it was actually a really remarkable mentor, my first real advisor in college physics, a person named Joseph Harris, who was an expert in classical general relativity. That was his great passion and what he'd studied for a long, long time. But by the time I entered college, Joe had cultivated really broad interests, kind of on the side. And he'd be reading, postmodern Italian poetry, or be reading, the notebooks of the German novelist Thomas Mann. I mean, he was just this remarkable, broad-minded person within and well beyond physics. Mm-hmm. And it was Joe who said to me, if you have all these interests, there's this thing called the history of science. You should go check that out. I said, I'd never heard of it. What did I know? I was, 18 years old. So it was really Joe, the classical relativist, who really helped open my eyes to a second field that I very rapidly fell in love with and get to pursue to this day, the history of science. So Joe connected me or pushed me to go meet two actual historians of science at the campus I had just begun my studies. They very generously took me under their wing. So as an undergraduate, I did sort of like a double major in physics and in the history of science. On the physics side, I delved more and more into early universe cosmology, learning about the still relatively new ideas about cosmic inflation, origins of large-scale structure, all these kind of very cool ideas that we could use, that we could try to address using the tools of things like quantum field theory, especially quantum field theory in curved space-time, which has its own kind of beautiful formalism to it. I got a little taste of that even as an undergraduate and was able to do, my undergraduate thesis on cosmic inflation and so on. And then as my undergraduate years were passing along, I met a few people by that point who had done this strange sounding thing where they had gone to graduate school and done a PhD in a scientific field and a PhD in the history of that scientific field. So one of my undergraduate mentors on the history side was Naomi Oreskes, still a very dear friend. And Naomi had done, by that point only recently completed, a PhD in geology and a PhD in the history of earth sciences. And her history advisor had been Peter Gallison, another very dear friend of mine. Peter had done a PhD in particle theory, essentially beyond standard model particle theory, and a PhD in the history of modern physics. And so I figured, well, 2 points define a line. There's at least two instances. There are more than only those two I've come to learn. But with their example in mind, I wound up applying to graduate school to do both theoretical physics and the history of science with their support, and I was lucky and able to do that. So for my PhD, I did a PhD in theoretical physics and a PhD in parallel in the history of science. And on the physics side, I continued to just explore more and more this early universe cosmology, these ideas about things like cosmic inflation. And luckily for me, my main thesis advisor became Alan Guth, who had helped, of course, to invent this whole body of work. And he, again, remains a very dear friend. And now we run a research group together. It's kind of a dream come true.
Right.
So anyway, from undergraduate days through my PhD, I've been really immersed in cosmic inflation. We can, of course, talk more about that. And so I didn't work on primordial black holes right from then. Other people were, even in the 90s, working on them. They were not such a central topic then. I had other interests that I pursued. My dissertation was on how would inflation have come to an end. So this era we can now call post-inflation reheating, which is really sort of setting up the conditions for the standard Big Bang model. Lots of fun, juicy stuff to study. And I was really having, frankly, a lot of fun with that. And then many years later, I kind of came around to an idea that I say some people had been pursuing for quite some time, that during this phase of cosmic inflation, where we know, and we got very good at calculating the expected spectrum of primordial perturbations, of essentially density perturbations, these are arising in our account now from quantum fluctuations of the fundamental field or multiple fields that were responsible for driving that phase of inflation, this phase of accelerated, very rapid expansion of space for a brief moment of time, but very rapid growth in size. And that already is the kind of framework within most of us think about the origin of large-scale structure generally in our universe. Why are there clusters of galaxies and then huge voids? There's a remarkable inhomogeneity in the universe across length scales on the order of, say, tens to hundreds of megaparsecs and below. And if you coarse grain across still longer length scales, the universe looks remarkably smooth. How do we account for this smoothness giving way to structure? What had seeded that structure? And that was a pressing problem from the 70s and 80s and well into the 90s and beyond. And cosmic inflation provides a, I think, really elegant framework to try to begin to answer that question, remarkably, by saying these things ultimately come from quantum fluctuations of the sort that we otherwise study in sort of other classes and other laboratories, whose wavelength was stretched to astronomical scale during this very rapid but brief period of stretching of accelerated expansion called inflation. So we already had to get very good and very careful at calculating the spectra of primordial perturbations during inflation to compare with high precision measurements of the cosmic microwave background, and now many more measurements that we care about. And so, as many people had been wondering for a long time, could that same basic process during inflation have led to amplification of a still sharper, higher peak on much, much shorter length scales of quantum fluctuations that could actually induce gravitational collapse? So the ones that I was used to studying that we want to think about for the cosmic microwave background, those are necessarily of a very small amplitude and very, very long wavelength after they get stretched during inflation. And the idea was, could that same phase of the early universe if there were some distinct dynamics later during inflation, but before the end of inflation, long after the perturbations we care about for the cosmic microwave background had already done their thing and been stretched far outside the Hubble radius, could there be other dynamics during inflation that could lead to a much sharper peak of these primordial overdensities, curvature perturbations, that could then cross outside the Hubble radius, a little while later come back inside the Hubble radius, and induce collapse directly to a black hole? That's that direct collapse that I mentioned a little while ago that would short-circuit the need for stellar evolution. Could black holes form because there were very strong, kind of likely narrow peak but high amplitude fluctuations of essentially the quantum mechanical nature that got amplified late during inflation for reasons, again, we'd be happy to dig into if you'd like, and then those could collapse to form a population of black holes, and then those would have sort of different, some sets of different properties compared to stellar collapse black holes that astronomers had gotten very good about thinking about in the interim.
So there are two directions here I want to take it.
Good.
I'm not sure where to go. Okay, for one, I want to rewind and ask about your colleagues who went into the history of geology, for instance.
Yeah.
And then also studied geology. Same, so you did physics. So history of X, but also studying X.
Right.
Is the history of X in service to studying X? Or is it just something to appreciate in and of itself?
That's a great question, Curt. So the person I mentioned who did the history of geology and was trained and was an active geologist for many years is Naomi Oreskes. She was one of my very important undergraduate advisors. But your question is more general. I think you're right. For a long time, in my own thinking, I thought they were both wonderful bodies of knowledge about which I was deeply curious and wanted to learn more. I didn't think that either was necessarily in the service of the other, except in some limited way. So, for example, my historical interests then as now are fairly recent physical sciences, sort of 20th century and even often, last half century or so, pretty recent. When, as you know, a lot of work in modern theoretical physics got pretty complicated, pretty technical. So I wanted to make sure that as an historian, I could follow what the people were doing in the 1940s, 50s, and 60s, and that meant making sure I had my own chops, sharp, that I could really follow not just the published and polished research articles in the journals, but the more messy notes, the correspondence, the summer school lectures, the kind of incomplete thoughts that sometimes are captured on paper as well that I found just really fascinating. I want to make sure I could do justice to what they thought they were doing and why. So that meant I had to make sure my own physics training was adequate to make sense of what they were doing not so long ago, without, while being on guard, about falling into a kind of anachronism or presentism. Well, we now know this about the behavior of quarks or fill in the blank, which they didn't know then. So you want to make sure you don't actually start reading things into the past just because they seem more obvious or self-evident now. It's a little bit of a balancing act, and one that frankly I enjoy. I want to be careful not to misrepresent what people thought they were doing in the 1940s, 50s, 60s, or before or after. But I also want to make sure I can kind of, so to speak, read the language. I want to make sure I'm conversant with what was likely on their minds, why they pursued this calculation. Oh, look, they made an error on page 3, but I get it. Here's why that came up. So it's in that sense, the physics was in the service of my history of science in a kind of, let's say, capacity sort of way. But I didn't think that one was otherwise deeply informing the other in either direction. And maybe later on we'll get to talk about a pretty fun counterexample, which I didn't expect. But the preview for that is that I wrote a book on aspects of the history of quantum entanglement in Bell's theorem. As an historian, I just was fascinated by the topic. Who cared about that topic, when and where? Why was it pursued in some places, not others? Just as an historian, I wanted to know more about the history of people grappling with foundations of quantum theory, including Bell's theorem and entanglement. So I wrote that as a historical, kind of exercise, and I had a lot of fun doing it. Dug in with everything I had to find the right sources. Just really great fun. And then after that, began talking about that topic with some of my young physics colleagues, and they originally realized, and then I was lucky to join them in the next steps, that given what we know now as astrophysicists and cosmologists about the large-scale structure of the universe, we could actually go back and imagine doing new types of tests of Bell's inequality in novel ways to address loopholes that had been identified, I'd learned about as an historian, that had been identified in the literature 50 years earlier. So that was one where the historical work actually helped catalyze a whole new multi-year research program that I, again, just had an amazing amount of fun pursuing. This is what became the cosmic Bell experiments using quasars and all that. So we can talk about that. But that's an example where it went in the direction I didn't expect, where a really kind of in-depth book-length history study, 350 pages, 1,000 footnotes, like all the good, juicy history stuff I worked so hard on, that actually helped lead to new questions for when I put my physicist cap back on. Typically, until that time, I'd kept them as, let's say, parallel pursuits and tried not to let one kind of bleed into the other too much.
Why do you have to try to not let one bleed into the other? You mentioned an example of quarks that in the 1970s or so on, we know quarks do this and that, or 1980s, or what have you.
Yeah.
And then you're reading some material from the 40s, and you said it's easy to read into it quarks, something like that. Can you give me an example?
Yeah, that's right. It might not be quarks per se, but let's take the topic of renormalization. So my first book as an historian, coming out of my history dissertation, was on the history of Feynman diagram techniques in quantum electrodynamics during the early stages of what comes together as renormalization. Well, as you know, people have thought about renormalization in quantum field theories lots of different ways over time. That is not a stable target. And so by the time we get into things like the very different view from, let's say, a more modern perspective with effective field theories, where we deal with non-renormalizable interactions all the time and don't break a sweat over it, right? That somehow the status and the role of renormalization is really quite different to a working theorist today than in the 1940s or really into the 1960s and early 70s. That's one example. Then the actual techniques of performing renormalization have changed. So in the early days, they weren't doing, they were very rarely doing, dimensional regularization. They're doing other kinds of techniques. So I want to make sure, what was their toolkit? Why did they think that was a productive way forward? What did they get stuck on? And not always be second guessing, but wasn't this answer obvious? Because it wasn't obvious, and this took generations, right? That's what I mean. So I don't want to, kind of misrepresent the path that seemed obvious to them at the time, because it takes much more time and many more, pairs of eyes and hands for where we are today to have come about.
Okay, this is interesting.
Yeah.
Had Dirac lived after the Wilsonian Revolution, do you think he still would have said renormalization was sweeping infinities under the rug?
It's a great question. So of course I don't know, obviously it's a counterfactual, but it's interesting. I don't know if the EFT framework would have struck Dirac as sufficiently beautiful. It might have. There are some things that I find aesthetically amazing about, RG and RG flow and all this new, more modern way of seeing it. But, Dirac, and he wasn't apologetic about it. He had a very explicit kind of aesthetic sensibility with his very austere mathematics. And I don't know if this would have met, his approval or not. It's an interesting question. I don't know.
Now, I don't mean whether he would have found it beautiful or not. I mean, would he still have found that you can get finite answers doing something with infinity? What would his view of that be after Wilson?
That's what I mean. It's a good question, but I'm not sure if he would have found the EFT or RG framework sufficiently beautiful, because for Dirac, beauty really was often a criterion for truth or for likely truth. And as he often was led by this sense of the kind of powers of the mathematical formalism, and the more bare bones, the better. He was famously a person of very few words himself. He barely spoke. These kind of stories that still resound. His, amazing textbook on quantum mechanics, still in print, first published in 1930. That's a pretty good lifetime for a book. It's very sparse. I mean, he doesn't want to get lost in a lot of verbiage, and not just words. He wants the mathematics to be kind of as crisp and clean as possible. And whether he would give the gold star to the most modern techniques today, it's hard for me to judge. I don't know. Yeah.
Okay, here's a fun counterfactual.
Yeah.
So Dirac famously said to Feynman, "I have an equation, do you?" Now, what if Feynman had retorted a couple of years later, "I have an integral, I have a diagram, do you?" What do you think Dirac would have said?
That's a good question. So I don't know that Dirac would have been so enamored of the Feynman diagrams, I have a feeling Dirac's reaction might have been more like Julian Schwinger's. Here, I'm guessing, right? But Schwinger might be a good proxy for Dirac in the reactions.
Great.
And as you might know, Schwinger was certainly in the early years no fan of the Feynman diagrams. He once sniffed very haughtily that Feynman diagrams brought computation to the masses, and that was not meant to be a compliment. So, if anyone can do this from drawing little cartoons, So Schwinger, I think, in a very Dirac-like way, was really enamored by this pristine kind of algebraic, kind of austerity. So I can imagine Dirac's reaction to Feynman's approach to have been maybe more like Schwinger's, and therefore maybe not so thrilled at first. Yeah.
Okay. What do quasars tell us about Bell's theorem? What is Bell's theorem, and what are quasars as well?
Good. So let's start with what is Bell's theorem. Bell's theorem is just a landmark of modern science. And I say not just modern physics. I think it's broader even than that for its intellectual sweep. It's merely 6 pages. It's a very elegant and brief journal article. It rewards rereading to this day. Bell, I think, was an exceptionally careful and disciplined writer. It's very clear. He wants to make his assumptions as clear as possible. It's clear. The article that we're talking about is called On the Einstein-Podolsky-Rosen Paradox. He's clearly referencing the so-called EPR paper, which had come out almost 30 years prior to that point. And Bell's article was published late in the autumn of 1964. Okay, so we just passed I guess its 60th anniversary, right? So it's been with us for a while. In this very brief paper, John Bell was concerned not so much about quantum theory per se, but about possible alternatives to quantum theory in the language that was then known at the time as hidden variables theories. So inspired by work by people like Albert Einstein and other architects of quantum theory, like Erwin Schrödinger, who came to be very skeptical and dissatisfied with what we might recognize today as kind of ordinary or orthodox quantum mechanics, Bell wondered, was there any way to put into a quantum-like framework a way of describing or ascribing to quantum objects definite properties prior to and independent of our measurement of them? And if so, could those properties also nonetheless obey what we might call kind of locality or local causality? Is there a way to make quantum mechanics look more compatible with relativity, where nothing travels faster than the speed of light, that's the locality, and in which there really are definite properties to little bits of matter that we can attribute whether we perform a measurement or not? And those were guiding principles that people like Albert Einstein thought should be part of any acceptable physical theory, and Bell thought those were awfully reasonable principles. So Bell's wondering, what would it take to develop a theory of the microworld in which those elements held true, where you could attribute properties to particles ahead of time before measurement, and in which local events yield only local outcomes. Local causes yield only local effects, let's put it that way. And he winds up formulating this very succinct, very elegant framework, and finds that in any putative theory of the microworld in which those two postulates hold, then there's an upper limit to how strongly correlated the outcomes of measurements can be on any pair of particles if they had been prepared together but since traveled apart. So he has in mind the EPR paper, Einstein-Podolsky-Rosen. He's thinking about what we would now call pairs of entangled particles, and he's wondering if a theory of nature is going to have these very reasonable sounding attributes, objects have their own properties, nothing travels faster than light, then what are the implications empirically for things like performing measurements on pairs of particles that have traveled in opposite directions far apart? And what he derives as an upper bound, that's why it's an inequality, on a measure of how correlated the outcomes can be, even in principle, on measurements and questions we might ask of each of those particles. If the theory describing them obeys sort of Einstein's preferred postulates, he finds there's an upper bound, and then he goes on very quickly to show a now standard calculation in ordinary quantum theory. The quantum theory predicts stronger correlations, that if you prepare particles in a particular quantum state, let's say, a quantum singlet state for two particles, a classic entangled state, shoot those particles in opposite directions, perform measurements in different bases, different choices of what to measure on each side, that for clever choices of the quantum state and clever choices of the measurements to be performed, the outcomes of those measurements can be more strongly correlated. They'll line up much more often, dramatically more often, than any Einstein-like theory could ever allow. So that quantum mechanics does not obey this conjoint pair of postulates of basically what became known as local hidden variables. So that's pretty amazing. And he also says, now he was a theoretical physicist, but he realizes this is in principle something that could be measured in a laboratory. So this becomes known as Bell's inequality or Bell's theorem, such that there's an upper limit to the degree of correlation and behavior of particles if they're obeying these local causal relationships. And then several years go by before pretty much anyone pays any attention. One of the first to pay attention was the then very young experimental physicist John Clauser, who got very excited about this. He saw the implications right away. He was a PhD student at Columbia University at the time in the late 60s, and was very actively discouraged by his PhD advisor to pay any attention to this. It was disparaged as sort of mere philosophy.
Why?
I think the general question or the topic of the foundations of quantum theory generally, let alone very specific topics like Bell's theorem, were really out of favor, out of fashion throughout the physics community, especially in the US, though not only in the US at the time. I've written a bit about why I think that was the case. I think it has as much to do with intellectual trends as with institutional changes in the way physicists were being trained coming out of the Second World War. And again, I'd be happy to talk about that. But for a confluence of reasons, Clauser was of that generation, of the few generations that were actively discouraged and sometimes really in very strong terms from pursuing any of these questions at the foundations of quantum theory, including Bell's inequality. So Clauser then finished his PhD on a different topic, got his first postdoctoral appointment, and then kind of was curious to go back to this question that had now been lodged in his mind for 3 or 4 years. Could one really do an honest-to-goodness laboratory test of this Bell's inequality? After all, he was, by that point, a really very well-trained experimental physicist. So he wrote directly to John Bell in 1969 and said, has anyone done this experiment since then? I was told not to. Has anyone done it? And Bell wrote back with great excitement, saying it was among the first questions he's gotten from any physicist in the world about this work.
Wow.
4 years later. And Bell confirmed no one had done the experiment. Few people showed any interest at all. It would be amazing to do it. And as famously as Bell concludes his private letter to Clauser, if you find results that are different from quantum mechanics, that would shake the world. That's the phrase that Bell had used. The stakes seemed high. So Clauser was fired up, and he teamed up with a small number of like-minded colleagues to pursue this. And again, happy to go into more of the history, but that was really that's the kind of Bell's inequality part. Okay. Now let's fast forward a little bit. It turns out that Bell's theorem is a mathematical theorem, which means it depends on starting assumptions, right? And so do those assumptions hold in the real world? If you're going to do an experimental test, you have to show that your experiment is consistent with the starting assumptions and not just that you found some results any old way. And so what Bell himself and Clauser and others like Abner Shimon and a whole list of people in the mid-'70s began to realize and identify is there are all these kind of what came to be called loopholes that have to be addressed in any given experiment if you're really going to conclude that the strong correlations that you presumably are going to measure are because of a violation of Bell's inequality. That's to say, there are all kinds of subtle, sometimes weird-sounding scenarios in which a perfectly Einstein-like theory, perfectly consistent with local hidden variables, could yield these very strong correlations. One obvious one that Clauser and Bell themselves wrote to each other about, right, in the early years of this, would be if information could be kind of flowing throughout the experiment, if information could be leaking from one side of the test to the other, if one particle is measured here, let's say particle A is measured here, and then enough time goes by so that a single light signal could have traveled from here to there, just at the speed of light, nothing fancy, and then later you measure properties of the second particle, well, maybe there's room for coordination of the outcomes because it was sharing of information. If I measured this, I asked this question here and got this answer, make sure yours lines up.
Yep.
Now, and so that's what became known as the locality loophole. It's very hard to address experimentally. In the early years, it was really technically a great challenge. But they realized if you don't take that into account, then you're not proving a violation of Bell's inequality if you nonetheless find strong correlations, if you don't have the right space-time arrangement of each relevant event in your experiment. They play these games over and over again throughout the 70s. Another one that they came up with that Bell himself had overlooked, and it was pointed out by people like John Clauser, Abner Shimoni, Michael Horn, about a dozen years after Bell first published his theorem, published in 1976, in a little out-of-the-way place, a little newsletter, was something that comes to be called today the freedom of choice loophole. It has other names. That's what it's often called. This is not about the flow of information during a given experiment. Did detector A message detector B? But instead, it's about shared common causes. Could there have been any subtle influence or event that you otherwise hadn't taken into account that could have nudged or previewed the series of questions to be asked at each detector in advance without changing what it can do, even if you know what questions will be asked when, and then could have communicated that in advance to the source of entangled particles before the particles are emitted? In that case, it's like getting a copy of a pop quiz the night before, right? If you know exactly the order of what questions will be asked when, then you and your twin at home can say, okay, this question's going to hear, let's make sure our answers line up. Now they leave on the school bus stop. So it's no longer mysterious. It's consistent with Einstein's principles to have strong correlations. If there was some flow of information, not during the conduct of an experiment, but from some shared causal common cause before. And so that's what got my colleagues and me really excited. That's what we wound up thinking about after I'd written this book on the history of entanglement and Bell's theorem. And this was with Andy Friedman and Jason Colicchio originally. They were very good friends in graduate school. Andy had just come to MIT to start a postdoc with me, working on other aspects of cosmology. We thought we'd work on dark energy and stuff. But so Andy read my history book and got kind of intrigued by it, and we all began talking about could we address this really stubborn, the kind of last of the most stubborn loopholes in Bell tests, using what we now know as astrophysicists and cosmologists about the large-scale structure of the cosmos since the Big Bang. This point in space-time could not have shared a single light beam with that point in space-time. That kind of question, which is something that's kind of bread and butter for cosmologists today, wasn't so common or certainly not as well known or constrained in the 1960s or 70s. So we wrote up a proposal, a whole article wound up coming out in PhysRev Letters, saying if we use very distant astronomical objects like high redshift quasars on opposite sides of the sky, and we trigger in real time on some measurement of that astrophysical light, let's say quasar A over here, its light was emitted most of the history of the universe ago. Mm-hmm. It's so far away from us now. That the light we measure now in a telescope had been traveling for 8 billion, 12 billion years out of a 14 billion year universe, that kind of thing. You measure it in a tiny fraction of a second here on Earth, and you perform something like the color of that light. Is it more red or more blue than average for that quasar? So you do some prep ahead of time. Here's the typical spectrum for that quasar. Is the light you measure right now more red or more blue than that average one? Okay. Do the same exercise with a different, very carefully chosen quasar on the opposite side of the sky, whose light is coming toward, can be measured at detector B. These are now separated on the face of the Earth. And likewise ask, is that light in that tiny microsecond more red or more blue? You perform these real-time updates after a pair of entangled particles are prepared in your earthbound laboratory and sent on their merry way. So the choice of what measurement to perform was not knowable even in principle at the time the entangled particles were emitted.
Interesting.
So sometimes people get a little confused. They think we're measuring entanglement from the sky. I wish. That's also a cool question that I'm interested in. That's a separate thing. Here what we're doing is using as thoroughly unentangled, as uncorrelated random bit streams as possible.
So it's just a way of you saying, look, we need distant observers or distant people to choose the measurement. Let's use the quasars.
And that's right, in a way that information about that choice could not have been previewed or whispered in the ear of any other part of the experiment ahead of time. because
Right.
that one bit of astrophysical light was traveling for 8 billion years, for 12 billion years. We even had to make the alignment very careful so the causal wave trains of one could not have reached anywhere any other part of the experiment in time. So really, frankly, very lovely relativistic astrometry, basically, to say that what's the information that could possibly have been gleaned from that quasar now about this quasar photon. And that's a way of shielding anything about the choice of measurement to be performed at detector B from either the source of entangled particles or detector A, and vice versa. So it really was to say we want the choice of measurements to perform, not to have any possible kind of cross-coordination or any statistical correlation with each other, but especially not with the source of entangled particles. There's no way, no one could have gotten the quiz ahead of time. There's no way that people got because the questions for the quiz weren't even written until after the particles left their laboratory to start their journey.
And just a moment, the choice of a quasar, other than some other extremely distant object, the choice of the quasar is why?
Good, because we knew our optical astronomy friends have gotten very good at performing very rapid cadence, precise measurements of light from quasars. So we were able to, we proposed this in a theory paper, right? Luckily, both Andy and Jason had very strong backgrounds in observational astronomy, which I do not. But we wrote this first as a proposal saying if you had a telescope with this size mirror, you'd count this many photons per second from an appropriately distant source, it would be feasible to do, right? And then we were extremely lucky to get to pitch this idea to Anton Zeilinger, just a renowned kind of wizard in the field, expert in quantum optics, and a lifelong, expert in testing topics like Bell's inequality and putting quantum entanglement to work. So Anton, we pitched this to Anton. He got very excited and enthusiastic, which was just, that'd been a dream come true. And so then we were able to secure some, frankly, modest funding from the National Science Foundation. Anton secured funding from the Austrian Academy of Sciences. He's based in Vienna. And so we put the collaboration together. We did a pilot test in Vienna with bright Milky Way stars and kind of hobby-scale telescopes. We literally took a copy of Sky and Telescope magazine when Anton was visiting MIT, turned to the back page, said, Anton, buy us 2 of these, please. 8 to 10-inch simple hobby telescopes would be fine for the pilot test. We do bright stars. They shoot out gajillion photons a second. We just want to prove that we can do the electronics and timing right. So we did that in Vienna, produced already a remarkably improved experimental test of Bell's inequality, because the most recent time when there could have been any coordination among local factors to account for these strong correlations that we measure among the entangled photons by something other than ordinary quantum mechanics, we pushed that back to be something like 600 years. And until our experiment, the longest that had been pushed back was like a millisecond before a given experiment. So we went from 10 to the minus 3 seconds to 600 years with our pilot test, with our cheapo pilot test, which is a great thrill. Many orders of magnitude. And on the strength of that, Anton in particular was able to persuade the telescope operators on the island of La Palma, the Roque de los Muchachos Observatory on the top of the island of La Palma in the Canary Islands. That has some of the largest optical telescopes on the planet. And in particular, it has 2 of the medium-sized ones, 2 4-meter optical telescopes that we're able to commandeer for several nights, all night, even though these are in such high demand for the astronomers. So because the pilot test had gone well and we went on the astronomers off season, we got time on these telescopes. And again, the idea there was to use 4-meter telescopes, with roughly 13 feet across. You can collect light from very distant, very dim objects like these high redshift quasars, the light that had been traveling for most of the history of the cosmos. So that's really what it came down to. The Anton's group was able to do extremely rapid measurements of the relative color of each quasar photon. That's something, as quantum optics people, they could filter on color extremely rapidly, knowing what the optimum would be. So a little far off, higher or lower frequency, they could measure that in a tiny fraction of a second. They could then actuate with something called a Pockels cell. Given the outcome of that astronomical measurement, they could then, because they're wizards at this, could literally rotate and change the basis within which an earthbound entangled photon would be measured. They could change the polarization basis, something called a Pockle cell, that could change every kind of half of a microsecond. So then the challenge is to have the baseline be long enough that the travel time for the entangled photons is several microseconds, which means you have to be, on the order of kilometer, because light travels so fast. You need to be able to make an astronomical measurement, physically change the instrumentation, change the measurement basis in which you'll measure that incoming entangled photon, and do it all after those entangled photons had already been emitted. So they had no kind of foreknowledge of the particular measurement to which they'd soon be subjected.
Man, what's most interesting to me is that you along with some other people, and a few $1,000s, were able to improve upon a previous result by several orders of magnitude.
It was a joyride. And we couldn't have done it without the team. So part of what I enjoyed so much about this was, again, like we were saying at the beginning, I got to learn all kinds of things I didn't know much about before. I have no training in laser optics. I still know not very much, but I knew more than I ever did, thanks to working very closely for close to 5 years with these amazing friends and colleagues, the ones for whom that's their expertise. Even on the theory side, I had studied Bell's theorem as an undergraduate. I got totally excited about that early on. That's partly why I wanted to write that history book, as a later scholar. But I'd learned, the kind of textbook version. I knew how to do the simple calculation show that quantum mechanics predicts violations. But to really, really get into the guts of Bell's inequality and the loopholes and all the thought that people put in on the theory side, again, that's a very advanced, developed body of knowledge that's sort of newly relevant in ways that I had no inkling of when I was an undergraduate, for things like quantum encryption and quantum information technologies more generally. So it turns out we often now use Bell tests to confirm the security of a quantum encrypted channel. Well, okay, what if your Bell test is susceptible to one of these loopholes? Either because nature behaves differently than we thought, or because you actually have to worry about a person who's actually trying to hack your system and fool you. So identifying these loopholes for Bell tests took on an importance that I had no inkling of ahead of time for many areas of physics I find really exciting and beautiful. That gave me a chance to learn more than just a little, enough to write a couple of good papers on it, at least, in partnership with friends and colleagues for whom that was more their daily stuff. So I don't want to say like I'm a gadfly, and I had some of those tendencies, but it was an opportunity to go learn pretty hard stuff, certainly hard for me, that was well beyond what I've been trained in, through all my years as an undergraduate PhD student and even as a young faculty member. And that the joy of a new learning curve is pretty amazing. This stuff is cool and hard, and I think I can do it, but let me try again. That feeling of making sure I'm not just getting stuck, doing what now feels familiar. In hindsight, I've been able to do that a couple times over in my career, and I find that just really, really important for my own, not just my own curiosity, but feel like I think I know more about the world. I think I have tools with which to try to explore questions I wouldn't have even posed before, and that feels really very exciting.
Okay, so let's get to this new learning curve.
Good.
New as in the past decade or so.
Yeah.
With primordial black holes.
Right.
So please tell me how primordial black holes connect to other areas of physics.
Well, many different ways.
Especially the unexpected ways.
Yeah, good. Let's start with the more expected ways. And so that's how I got into them in the first place, or it was more expected for me at least. As we talked about before, most of my physics training had been on early universe cosmology, topics like cosmic inflation. I was already well practiced at calculating the perturbation spectra. What's the kind of degree of primordial lumpiness, to speak a little loosely, that we would expect from various models of inflation, compare with observations of the cosmic microgravity. That was my bread and butter. And I love it. I still love it. I find it amazing that we can do that. And so I began thinking my entree into primordial black holes, for me, it was familiar to many people by then, but what brought me into it was think about models of inflation where they might have something else that happens near the end of inflation beyond just a kind of vanilla, what we often call slow roll toward the end, where you could sort of build a model, hopefully a well-motivated model, with ingredients that we think should be there anyway from fundamental high-energy physics. And would those provide the kind of different dynamics toward the end of inflation that would lead to this very large dramatic amplification of the fluctuations that could lead to black holes. So for me, that meant thinking about models of inflation that move well beyond the kind of single field toy models that are very familiar and very helpful, but ultimately really, I think, a cartoon. And they don't fit super well, I think, with the better articulated ideas from whether they're coming down from string theory or any kind of UV complete ideas about, let's say, Planck scale physics, supergravity inspired or otherwise. So some of those ingredients include more than one scalar field, right? Even in the standard model, our beloved and exquisitely well-tested standard model, there are 4 scalar fields in the standard model. There's the Higgs field and the 3 Goldstone modes. At lower energies, high for us, but like at the LHC and around that, we tend to go into unitary gauge. We talk not about Goldstone modes, but about sort of the massive vector bosons like the W's and Z's. Mm-hmm. We know ultimately those are really coming from, that is to say, the masses are coming from these sort of eaten Goldstone modes. So what had been massless vector bosons become massive, and then you have 3 polarizations. That usual story is, I think, amazing. But the point is, we often get away with dealing with one scalar field in the standard model, the Higgs field, and we treat the Goldstones as polarization states of massive vectors, the W's and Z's. Fine, that works great. It's perfectly self-consistent. But at very high energies, unitary gauge is not renormalizable. And if we want to talk about energy scales that are below the Planck scale, but much closer to that than to, kind of GeV or TeV scales, if we're not doing LHC physics, then in the renormalizable gauges, the Goldstone modes stay in the spectrum. So just the standard model is a multi-scalar field theory when described self-consistently at high energies. That's already cool. And then again, as you and I'm sure many guests on your show have emphasized, every known beyond standard model theory building introduces more and more scalar fields. Maybe it's an axiverse, maybe they're moduli, who knows what they are.
Sure.
But there's no shortage of scalar fields once you go even beyond the standard model. And in the standard model, as I say, it's already a multi-scalar field, framework. So one of the things that I find really important or helpful in thinking about inflation is to build models that have more than one scalar field, since at very high energies and very early times, that seems relevant. That seems like a relevant ingredient in the spectrum. Okay, that's part one. Another ingredient that I think is more often overlooked, but I think it's actually really important, are what are called non-minimal couplings between the scalar fields and the space-time curvature. That's to say, at the level of the action, a direct coupling between the scalar field and the Ricci scalar that describes our space-time curvature. These have been thought about for a long, long time in even classical GR. They're required, they're induced by quantum loops, even if you don't put them in by hand. They show up from all kinds of compactification schemes. You are starting from some sort of UV physics that's beyond standard model. Another fairly generic ingredient would be these so-called non-minimal couplings. Or if you want to be agnostic and go back to this EFT, effective field theory view that we talked briefly about before, these are dimension 4 operators. How do you not include them in an EFT, right? So if you just start from writing down an EFT with all the self-consistent dimension 4 operators, then you write those down, right? And then there are words you can put around it. They're motivated by this or that physics. So that means I think it's really important to be building realistic, or at least better motivated models of inflation with at least those 2 key ingredients: multiple scalar fields, each with a nominal coupling to gravity. Okay, that suddenly is a playground that's different from the kind of simple cartoon-like single field models of inflation that hopefully can help us connect better to kind of to higher energy, potentially kind of UV physics. Okay, once we start doing that, one of the first papers I wrote on primordial black holes with a whole slew of wonderful colleagues and students was so that automatically, without putting anything else in but those ingredients, you automatically start getting these kind of directions in the effective potential. And your potential now is a multidimensional object. You can have phi 1, phi 2, and maybe more than those. There'll be directions for the evolution of that system that will yield exactly the dynamics that people had found in these single field constructions that will lead to a spike and primordial black holes. We didn't put those features in by hand. We knew to look for them thanks to these very pioneering works on single field constructions of the effective potential for inflation. But they just fall out when you start from ingredients that I consider better motivated anyway. We even went to the work, my colleague Evan McDonough did most of this part, of showing you really have a self-consistent UV embedding. This really flows from a certain supergravity construction. This is not the, but a well-motivated model of the very early universe. And for free, we find these regions in which you should get this unusual behavior before the end of inflation, where you would expect a large amplification of the quantum fluctuations. Inflation ends, those cross back inside the Hubble radius. There's such localized overdensities, bang, you have made a population of primordial black holes. That's one example where, again, I hadn't worried very much about Kähler potentials and some of the machinery of supergravity. I got to learn enough to be able to participate in this paper and then help with other parts, because I've been thinking a lot about nominal couplings and multi-field. Okay, so that's step one. One way that primordial black holes has led me to think about other areas of fundamental physics, in this case, closest to home base for me, but even that a bit of a stretch, right?
Sorry, before you get to part two.
Sure.
Okay, you mentioned that with one scalar field, there's some prediction or there's some model, and then you said you were able to get to it from multiple scalar fields, and you felt like these multiple scalar fields were more well-motivated. But it sounds like you're introducing more ingredients. Why would you want to recover something that someone can explain with 1 when you're explaining it with 5? How is that better?
So wonderful question. Good. Partly because to get this to work, to actually make primordial black holes with single field models, you require an awful lot of fine-tuning, which is not what cosmologists like, typically. And in particular, what that meant in practical terms, for each of these very clever, single field kind of worked examples, proofs of principle, you get as extreme an amplification of the perturbations as you need to cross a threshold to induce gravitational collapse. So you really need a very large amplification of these fluctuations. To get that, you had to have at least one dimensionless constant, one parameter in your Lagrangian, tuned to some really uncomfortable degree.
Sure.
Like 6 or 7 decimal places. So that doesn't seem like that's just going to happen on its own. So part of what got us excited is we were finding with these multi-field constructions, you get these dynamics while reducing considerably the amount of fine-tuning of any given parameter. So one motivation was we think it's more natural anyway to think the universe was filled with multiple scalar fields, nominal couplings. And then we started finding that we actually use fewer parameters than predictions. I'll come back to that in a second. We're not overfitting. We need to fit 8 numbers to percent level accuracy with 5 free parameters. And we don't want to tune any parameter to such an extreme degree. So suddenly, we're in a different regime than a single field construction, which can do it in principle, but what looks, again, we might say, unexpected or unnatural or fine-tuned. And that's not knocking those papers. Because all those cool constructions existed, we knew kind of what to look for in our expanded, toolbox. That leads actually to my next point. Another thing, my first and so far only Markov chain Monte Carlo simulation, which is bread and butter across so much physics, an amazing tool, right? My first one that I got to really do with the help of an amazing set of co-authors, was to subject these multi-field models with a couple free parameters, throw them into an MCMC, let, lots and lots of these so-called walkers in the computer solve the equations over and over again, compare the predictions with a very precise body of observational data, and then find what are regions of parameter space where this works. Do you just get lucky once, or is there a kind of trade-off between parameter degeneracies? Which is another way of asking how likely or unlikely do we think this is? And getting toward a kind of Bayesian, it's not quite formally Bayesian, but in terms of kind of explanatory power. You don't have to get lucky with all your parameters lining up once. You, in fact, see trade-offs and kind of blobs in these corner plots, where you would match all the high-precision measurements of the cosmic microwave background and make black holes, and the masses would be right for dark matter, down the list, with a handful of ingredients, fewer than you're trying to match, no one of which has to be pushed so extremely into a corner. So, for me, again, growth opportunity, to put it mildly, incredibly powerful techniques like MCMC, and that's still within my own wheelhouse of early universe cosmology, multiple field, nominal couplings, dynamics, spectrum of perturbations, stuff that otherwise I knew about and had written about. The next one then was to ask, well, okay, these black holes would form at a very particular moment in cosmic history. If they're going to be much or all of the dark matter today, then we know, for reasons, again, I'm happy to talk about, there's a window within which their masses have to land. If they're too big, they're already ruled out for being all of dark matter. Maybe they're 1%, but not all of dark matter. If they're too small, they would essentially Hawking evaporate already and they can't be around today, but we need dark matter around today. So there's a window of about 6 orders of magnitude in mass, within which, at least as of what we know today from the various constraints, all of dark matter, in principle, could be accounted for based on a population of these primordial black holes, maybe formed from these inflationary perturbations, and their masses have to fit within a box. And the box is about 10 billion times smaller than a solar mass and below. So you go from 10 to the minus 10 solar masses down another 6 orders of magnitude from there to fit within that box. Okay. Turns out this direct collapse I mentioned, the way that you form black holes, not because stars form and they die, but directly from the collapse of primordial perturbations, the mass of the resulting black hole, the mass of these PBHs, if they formed, is really a clock. It tells you how large was the Hubble sphere at the time those black holes formed. These black holes form by swallowing most, but not all, of the mass enclosed within the Hubble radius at the time that they form. And that had been identified, again, many, many years earlier. And we know how the mass within the Hubble radius evolves over time because we know how the Hubble radius evolves over time. That's just saying how at what rate was space-time stretching after inflation. And we have very good checks on that. So suddenly, the mass of the resulting black holes, if they're going to account for most or all of dark matter today, tells us not only what mass they have, but when they must have formed. Because they had to be an appropriate fraction of a Hubble mass.
Sure.
That's a moving target. Bang. Now we know the clock when they had to happen. That's pretty cool. Well, it turns out to be all of dark matter. These black holes had to form really, really early, after the end of inflation, but long before Big Bang nucleosynthesis, which starts at around 1 second, long before the electroweak phase transition, which happens around 10 to the minus 12 seconds, long before the QCD confinement transition, which happens around 10 to the minus 5 seconds. We have these benchmarks in cosmic history that span the first second. It's amazing. We can slice and dice the first second with such precision. And these black holes formed way before each of those kind of milestones. So that means that the universe must have been filled with a very hot plasma of unconfined quarks and gluons. They're not yet bound into color-neutral states. They've not yet undergone the QCD confinement transition. Standard model, SU3, beautiful, QCD, at very high temperatures, it's an unconfined theory. And this plays into things like so-called asymptotic freedom and so on. They're weakly coupled to each other. They're not bound in color-neutral states. The universe is color-neutral. If you coarse grain over the whole Hubble sphere, or even you need to go even less distant than that, there's a balance among the color charges in any region of space, but they're not bound into, kind of hadronic states, the way they would be after around 10 to the minus fifth of a second. So these black holes are forming by scooping up, kind of shovelfuls, tiny shovelfuls of unconfined quarks and gluons, of QCD-charged, color-charged matter.
Wait, I'm not understanding. Are you saying that there are color perturbations that from afar it looks white, but then when you look closely, there's some little intensities of red or green or what have you?
You nailed it. That's exactly right, Curt. And I should say this thing, I didn't know that in any detail before the primordial black holes led me to this topic. Experts in QCD have known this for a long time. I hadn't worked in QCD. Here's another example where there's a body of expertise, including some of my very dear colleagues right at MIT. I could literally just walk down the hallway and say, hey, wait a minute, what should I be reading? What's the review article? Can you answer these questions? A lot of help locally, to be sure. But I was led to ask about what's called the Quark-Gluon plasma because I was following the black holes. They had to form really right then in time. The universe was filled with a certain kind of stuff. Unconfined quarks and gluons, go. Right now, that's my assignment with, again, an amazing partner, a colleague, a PhD student, in fact, Elba Alonso Monsalve, with whom I was working on this part. So the idea is, as has been known for many years, just as you say, at very high temperatures, the quark-gluon plasma is net color neutral, but has color charge fluctuations on a typical length scale. You imagine anything, it's probably not going to be perfectly pristine along arbitrarily short distances. And that's true for the distribution of charges in a plasma.
Right.
Very similar to even a classical electromagnetic plasma, as it turns out. It needn't have been that way. But partly because we're in this kind of asymptotic freedom regime, it behaves There are non-abelian corrections, but it's a lot like an abelian or like a U1 E&M plasma, which had been worked out by the wizards of this area over the course of the 1980s and 90s and refined since then. So it was there for me and Elba and others to begin to dig into. So the community of QCD experts, very high temperature QCD, this includes both theoretical work and now very fancy lattice simulations, QCD lattice simulations. They were able to show within a static Minkowski space, that's all they ever had to worry about, right? That there are these color charge fluctuations in the plasma, and it's set by something called the Debye screening length, which depends on the temperature of the plasma.
Debye?
Debye, like Peter Debye, the Dutch physicist from the 20s and 30s. So Debye had been working this out for classical electromagnetic plasmas in the laboratory as a theorist. And then this became a very well-known body of work to plasma physicists and so on. And then the QCD folks realized it's remarkably parallel to study this in otherwise a very exotic system of very high temperature quarks and gluons. So any charge you might measure on any given charged particle is screened by the screening medium. The degree of screening is set by this characteristic length scale, the Debye screening length. That depends on the gauge charge, the dimensionless charge, and the temperature of the plasma, essentially, and the numbers of gluons, the number of quark family flavors. But basically, it's a number times the temperature. The length goes as inverse temperature. So that had been worked out in Minkowski space. The first thing Elba and I then had to do was say, well, we don't want to apply it to a flat space-time or a static one. We want to apply it to all the glories of a bending, warping, curved background, because this is an early universe that's expanding rapidly, and we want to study it near a black hole, so you can have really significant space-time curvature. It should be not very much like Minkowski. So the first thing that Elba and I had to do then was learn as much as we could about the Minkowski space treatments of effective field theories of very high-temperature quarks and gluons, amazing, beautiful stuff that had been worked out by many people, and then some very nice pedagogical review articles, plus my friends down the hall. We could do it. We could dig in and do it with work, but we could do it. And then apply that to this scenario I've been talking about. What happens if a bunch of black holes start forming amidst that kind of medium, if that's the fluid that undergoes gravitational collapse?
Okay, sorry, just as a point here of clarification.
Mm-hmm.
So when primordial black holes are forming due to perturbations, these are matter perturbations? They're not just, so in Einstein field equations, you have something related to the metric and curvature on one side and the matter on the other.
Right.
So you could conceivably have perturbations of just the metric which produce black holes, but you could also have matter which sources the metric. So which one is it?
Both, because is a great point, Curt. What we have to do is work with gauge invariant quantities. And so what you just described is every one of the metric perturbations we write down, if we're not careful, is a gauge-dependent quantity. When we write down things like delta rho over rho, that's gauge-dependent as well. So on both the geometry side and the matter source side, if we're not working with gauge invariant quantities, we're very likely to fool ourselves with gauge artifacts. So again, very smart people decades ago, often in the context of inflationary cosmology, worked out a whole series of gauge invariant combinations, linear combinations of a kind of metric perturbation in a certain parameterization and a measure of a kind of delta rho. And we work with these gauge invariant curvature perturbations as an example. There are Bardeen potentials. Many of these that have stood the test of time. So what we're doing is essentially the answer is a yes to your question. You're right. You linearize Einstein's field equations, work to linear order in these perturbations, and then only work in these gauge invariant combinations, track the evolution of those. So we're confident we're not fooling ourselves with a gauge artifact, so to speak, from either side. So in that sense, these really are combinations of perturbations in the fluid and perturbations of the metric, and you work with a linear combination. So that's what we do, and so we could again work in the language of things like Debye screening length, and look at the distribution of color charge in this roiling hot plasma, which is not uniform on short length scales. Now, it turns out these black holes form from a really amazing process called critical collapse, which again was worked out 30 years ago, found by accident. The black holes form in a way that's a lot like a phase transition from StatMech. It's like you have a kind of order parameter and a universal scaling exponent. This is just another example where who would have thought that's going to show up here in studying black holes? It's absolutely, I think it's just gorgeous. This I think maybe Dirac would have liked. I don't know, but it seems so pristine and so beautiful, and it's very well tested now numerically and analytically. And so the idea is that you make actually a whole distribution of masses. The perturbations that cross back in, they form a mass distribution that has a very distinct peak. You make most of your black holes with this characteristic mass, and that tells you your clock. That's why you know it had to happen now and not later to make the characteristic mass fit within your box. But then you make a power law tail, a small mass tail. So you make fewer and fewer black holes of smaller and smaller masses with a rate of at which that falls off that again is controlled by properties of the fluid, by universal scaling exponent. What that means in practice for this is that whenever these perturbations make a whole bunch of black holes that are of size m1, you make a few of them that could be exponentially smaller. That means they're forming from the collapse of correspondingly smaller regions of space. And what Elba and I realized is that you could have some black holes at the tail of that distribution that form by swallowing up one, charge-correlated region of the plasma, where practically everything it falls in has charge red anti-green. It's mostly the gluons. Or blue anti-red, or whatever it's going to be. The gluons have their little charge vectors, lining up in our SU3 space within a region set by the length of the Debye screening length. Most black holes you make swallow so many exponentially large number of these regions, they're color neutral as well. Even though they're so tiny on human scales, they're much larger than the Debye screening length at the time of formation. So on this model, dark matter would be neutral, right? It would be electrically neutral, it would be color neutral. Dark matter would be inert and boring and acting gravitationally, which is what we want dark matter to do. But in the course of making most of the black holes there, as Elba and I trace it through very carefully, you'll make a smaller subpopulation that are smaller in mass, formed from the collapse of correspondingly smaller regions or volumes of space, within which the color-charged particles have their charges more or less aligned. So you make a subpopulation that can be extremely highly charged under SU3. And that's amazing. So it's a novel state of matter. This is having like 10 to the 13 charge units sitting within a black hole on top of each other. That's just amazing. So what do you do with that? So that leads to other questions about fundamental black hole physics, about how do you discharge such a highly charged, QCD object, all kinds of questions, and get loaded into the queue from following our nose to like black holes form early, the universe is filled with QCD plasma. Wait a second, we better learn about QCD plasma. You see, that's another example, a long example, of how much fun this is to track through, follow the black holes, build on some stuff that's known very well, modify it for the situation, and then that leads to still new questions that even our friends in QCD had never had to broach before.
Have you found any implications or violations of the no-hair theorem, or cosmic censorship, or even BPS bounds?
These are exactly the kinds of questions that now we're very eagerly pouring into. On the observational side, one thing we're really interested in is could this whole scenario be constrained or ruled out, or could you find evidence for it? Because these very, very tiny mass black holes with tons of charge, they would eventually Hawking evaporate. So I don't think those would be around anywhere near today. In fact, they probably wouldn't even last much more than a second. They form so early, a second would be a very long time to them.
Mm-hmm.
But if you have enough of them hanging around within one region of space, as late as 1 second, then they'll be emitting very high energy exotic hadronic states into what's supposed to be a thermal equilibrium of protons and neutrons that start to undergo Big Bang nucleosynthesis. So if you start messing around with the relative balance of protons and neutrons, you start tweaking the proportion of this isotope of lithium compared to that isotope of boron. You start potentially messing around with Big Bang nucleosynthesis, which is all about relative abundances of very specific isotopes. And others had looked into this idea for particle-based dark matter. If you have other, dark matter that could be decaying and shooting out energetic stuff into at the onset of Big Bang nucleosynthesis, you can look for observational effects or constrain such scenarios. Again, we can build on a body of knowledge others have worked out, modify it, and here it wouldn't be new fundamental particles decaying like a kind of particle dark matter scheme, as interesting as that might be. It would be perfectly standard model particles, only standard model ingredients in a perfectly well-described classical gravitational state, a black hole, that becomes our new ingredient. That could then be undergoing late-stage Hawking evaporation on the order of 1 second after the Big Bang. Could that be either constrained because it would have messed up too much BBN? Could it maybe help alleviate some of the tensions within BBN these days? Or what? So that's a more observational, it's a stretch, but something that we're curious to chase down. It also leads us to ask, much like you were asking as well, some really juicy fundamental questions about black hole physics. Black hole physics, I just find, I love it. And it's filled with some extremely beautiful theorems, almost all of which concern a single black hole in vacuum in an asymptotically flat space-time. As it turns out, there has never existed a single black hole in vacuum in asymptotically flat space-time. So this entire, and I say that not to disparage any of these amazing Nobel Prize-winning results, but again, the kind of body of knowledge in some areas of black hole physics, these pristine things like cosmic censorship, no-hair theorem, and others, they have typically been worked out in scenarios that don't really mesh very well with our universe, right? Because black holes aren't alone and space-time isn't asymptotically flat.
To be fair, in particle physics, you often say that the particle is prepared in the infinite past and then it's in the infinite future.
One does.
When you detect it.
That's right. Now, and because that's a clear shortcoming, people have worked out additional formulas like the so-called in or Schwinger-Keldysh formulas exactly to avoid that, right? Because sometimes that assumption really fails. I'm not sure we've caught up yet in the community on black hole physics to do the equivalent of that, just to your point, Curt, actually. What's the complementary formalism that might need to be developed to really answer these beautiful questions about hair, about no hair, or about cosmic censorship for scenarios in which a black hole is immersed in an active medium and no part of this necessarily becomes asymptotically flat spacetime? So that's something that it's really hard. Elba and I are working on that now. For example, we don't have any clear results, but that's the question. The question which we're led to by following black holes and the medium and so on is that. So again, it's a chance for me to learn some really cool physics and see, well, that's not quite what we need to answer these questions. The questions are driven from following the black holes. Let's dig in. What can we do here? Could we maybe try to contribute something here to this very beautiful body of knowledge I have such great admiration for? But because these particular questions seem not really to have been broached, or at least not really answered yet. Another great example.
Okay, so let's call this theory inflationary PBH theory, just to give it a moniker. Now, some people may be wondering, why is it that you're looking at the data today and saying, okay, what would the properties of the primordial black holes have to be in order for them to be dark matter candidates?
Good.
And then going to your theory here, why wouldn't it be that your theory here could give you indications about this direction in order for you to invalidate it? And the response may be something like, well, this isn't a single theory, it's a whole space of theories. And so what we can do is we can say, okay, what constraints would there be on this inflationary PBH side if we were to think that primordial black holes are what comprise dark matter? And then, okay, so now you've carved out a little niche here.
That's right.
Then you could say, okay, given that these are the constraints on that theory, are there signatures that we would expect from such a theory, from such a constrained theory, that we can then look for? Maybe it's not primordial black holes, maybe it's something else, but it would be an indication that we're in this parameter space.
Good. I think that's exactly right. And so just to say, the inflationary models, what I've described are families of models and regions of parameter space, not a model and a set of parameters. So exactly you say, the nature of the distribution of the black holes that result depends on the inflationary dynamics beforehand. So we've shown kind of existence proofs that with ingredients I consider realistic, with much less fine-tuning than before, than the single field, we can produce populations of black holes with kind of gross characteristics that are in line with what we want. The peak mass fits within this box, let's say, and that have, the tails and so on. But it's not uniquely picking out. It's showing there are production mechanisms that are congruent with other ideas from very high energy theory that don't require wishing come on a star to make sure everything worked out in some unnatural way. But that's different from saying this is the theory and the single prediction. It's, it does depend on which member within that family, what region of parameter space go. And it also had no way, that still doesn't tell us, do primordial black holes exist? And if they do, are they 10 to the minus 8% of the dark matter abundance today, or 100%, or somewhere in between? And so that really does require looking to the contemporary universe, or the recent universe anyway, and doing what my friends and I call kind of direct detection of black hole dark matter. It's not quite direct, but local detection. We've had 50 years of very heroic and very expensive efforts to detect particle-based dark matter with so far exactly zero compelling results. And again, I say that not to fault the people who work on this day in and day out.
Sorry, wait, particle-based dark matter?
Yeah, what if dark matter...
Oh, wait, sorry, I thought you said particle-based black holes.
No, right, no. What if dark matter is what most physicists, I think, would still expect, new particle or maybe a whole dark sector or family particle. Great. We haven't found any of them in any so-called direct detection experiments. And again, that's not for lack of trying. And the sensitivities of the experiments have gotten outrageously better. It's an amazing, effort that so far has yielded exactly zero dark matter particle candidates. Okay. So what's the parallel to try to figure out whether dark matter consists all or mostly of these primordial black holes? So that set, again, some wonderful students and collaborators and I are thinking about late universe local detection. And it involves things like gravitational perturbations, gravitational waves, and also ejecta. These things really would be undergoing Hawking evaporation. What can we look for that? So now I get to play with experts in cosmic ray experimentation, high-energy cosmic ray detection, experts from LIGO and beyond on gravitational wave detection, and as well as my own more local gang, were able to show that there would be a kind of predictable, countable number of these black holes that would fly through the solar system once every kind of 3 to 10 years, which is a pretty nice human scale cadence. They won't happen every month, but you don't have to wait 3,000 years to look, for an example. And when they do, if they have the mass of an asteroid, these so-called asteroid mass black holes, but the size of like a hydrogen atom, they're not going to hit anything. The odds of that are astronomically tiny. But you have a flyby and even a purely Newtonian impulse. You can do it more carefully with general relativity, but even Newtonian n-body gets you most of the way there, remarkably. To say a black hole whizzes through at 200 kilometers a second at, say, 5 astronomical units, that's a large enough sphere where you expect it to be, a couple of these hanging around and going on these kind of joy rides. And suddenly we have a remarkably well-instrumented inner solar system to look for very tiny but indeed measurable perturbations to the motions of mundane objects we track all the time, like the planet Mars. I don't know about tracking the planet Mars. There's another example. Follow the black holes, and now I get to learn about some other cool stuff, like ranging within the inner solar system. So I knew from actually some colleagues that astronomers had been doing laser ranging of the moon since the Apollo 11 mission, since 1969. So one of the first things the Apollo 11 astronauts did was put up special reflectors on the moon, retroreflectors. And astronomers can shoot lasers to those reflectors and very carefully measure the return. So we know the Earth-Moon distance with an accuracy of about 1 millimeter. That's 250,000 miles away, and we know the distance to the accuracy of 1 millimeter. That's astonishing. Because of 20 years of Mars, orbiters, rovers, landers, and some very long baseline interferometry, a range of techniques, astronomers know the Earth-Mars distance to an accuracy of about on the order of 10 centimeters.
Okay.
That's much further than the moon. And if the error is on the order of 10 or tens of centimeters, that's astonishing. So Mars is being tracked, and the Earth-Mars distance is being, kind of constantly calibrated, even as both are moving. And that's fed into some extremely sophisticated solar system dynamics models, so-called ephemerides models, run by a few groups around the world, where they're running sort of n-body simulations of 1.5 million objects that they track in the solar system, not just like the planets and the sun. Lots and lots of moving parts, and constantly benchmarking with the latest high-precision data from things like, tracking of Mars. So suddenly, if a tiny little hypothetical black hole that's part of the local dark matter density cuts through, sort of transects the solar system, it is likely to produce perturbations on the motion of Mars that will exceed its otherwise, very small error budget of where it's supposed to have been, measurably and not arbitrarily long after the flyby. So that sort of thing where could we get better at detecting basically gravitational perturbations to well-tracked objects within the solar system as a beacon, as an indication that something was a perturber that flew by. Now, that effect depends really only on the mass of the perturber. They're very far away. You can do n-body and not worry about, kind of tidal forces. And so what if it was just a mundane space rock of the same mass? So, okay, well, what's the expected background for that? It turns out there are online databases maintained by groups like NASA, the Jet Propulsion Laboratory, which have tracked almost 500,000 near-Earth encounter objects. In fact, they've tracked anything that got within 3 astronomical units of any planet in the solar system for the last 100 years.
Wow.
That's a great database. And they can do things like what's the inferred velocity and other orbital characteristics. And you can realize that the black hole path should be really disjoint from that entire distribution. So it doesn't prove it was a black hole if you see Mars wobble with a certain time signature, but it would be highly unlikely to have been any of the known and well-tracked objects for the last 100 years. That sets a baseline expectation. It's probably is not likely to merely have been a space rock, mundane space rock. And then if we can get better at reconstructing the path of the perturber based on the time series of the perturbations of the object we track,
right,
you infer the current location of that object. And again, astronomers have gotten very good at finding very small space rocks in the solar system, which have much smaller mass than these black holes would, but are not the spatial size of a black hole. They're rocks, so they could be tens of meters to kilometers across, and they'd be made of like rock. And so they'd have an albedo, they'd be typically trackable even optically. Again, it's not proof that we found that the lack of such a visual component means it was a black hole, but we have ways of saying there's an unusual wobble and no clear visual component. That's at least increasing the odds that it was a black hole. Then we can go a few steps further. If it's really a black hole, then some fraction of those would be undergoing Hawking emission today. So the black holes at the smaller end of this allowed range of masses, for which they could still be all or most of dark matter, should mostly be quiescent. They would be highly inefficient Hawking emitters. And in fact, that's where that bound comes from. If they were efficient Hawking emitters, if they were later in their lifespan and a smaller mass, then we'd be awash in cosmic rays that we don't measure. So you can actually constrain the fraction that would be kind of late Hawking emitter black holes. Nonetheless, there are extended mass functions. If most of the black holes are essentially quiescent in terms of Hawking radiation today, there's a distribution. Some of those would necessarily be smaller masses today, and those would be a little further along in their kind of evaporation life cycle. So what are the odds that you have a gravitational perturbation and, a certain, say, positron excess that would be consistent with Hawking emission from your perturber, things like that. And that would certainly not have come from, a mundane passing space rock. So that lets me play with some amazing colleagues with things like, what would it really take to detect, excess positrons? What really would be the time series signature for that? So we're not just fooling ourselves. Is that visible from existing experiments? Should we propose building new ones, right? So suddenly it's about like CubeSats and very sensitive clocks and laser ranging. I didn't do that in grad school. That's like amazing. With experts who know what they're doing, so I'm hopefully not just fooling myself, but a chance to build new collaborations, learn with new partners, and ask these questions because we're led by trying to follow this hypothesis of primordial black holes, which maybe they exist, maybe they're much or all of dark matter. How would we know? How would they show up in our cosmic neighborhood? Not just could we imagine how they might have been produced very early in cosmic history.
Okay, so the reasoning is that if the black hole was of the mass of an asteroid, but the size of a hydrogen atom, then it would bounce like a billiard ball would bounce off of Mars and just perturb its where it would have been. What about Earth?
Well, we don't even consider direct impacts. The odds of the cross sections is so incredibly tiny. So the odds of it hitting Mars, the Earth, or the Moon are essentially zero in the whole age of the universe. All we need is for this thing to have zipped by in otherwise empty space.
Okay.
2 astronomical, 3 astronomical units away from Mars. It's a large mass traveling fast. There's an impulse, even a Newtonian impulse, let alone a fancy relativistic one. There's a gravitational interaction at a distance, at an impact parameter that could be genuinely macroscopic, astronomical units. That alone is enough to make Mars wobble tens of centimeters, sort of off course. It's a self-correcting. The perturbations would damp over a long time period, but not so quickly that they wouldn't be visible from this very sensitive tracking. So we're not thinking about impacts per se. We're thinking about flybys, where the black hole just toodles on its way at actually a fairly rapid clip. But because it's now kind of not gravitationally bound, it's not coplanar, it's not in the ecliptic, it can cause very specific types of perturbations to visible objects we track very, very closely.
I see.
Yeah.
But what about the Earth? Why not if it passes by the Earth? Why are you focusing on Mars?
The main reason is because that's a great question, Curt. We first thought about the Earth Moon, or we have, and other people have written a paper about this, a lovely paper, both about Moon and also about the constellation of GPS satellites and related other systems. So, for GPS to work, the people need to know the instantaneous location of those satellites to sort of centimeter or tens of centimeter accuracy. That's so that we know where we are on Earth from when we get their signals. So we have 30 plus GPS satellites that are well tracked. Here's the reason why that I think gets more complicated. We thought we had a cleaner signature, because if it's that close to either the GPS satellites or even to the moon, then you really have to worry about tidal effects, about local deformations. There's not n-body. It's not point masses at a distance. Whereas if a black hole passes far away from Mars, those are two point particle-like interactions, and Earth-Mars system is much more reliably a kind of two-point system. There are highly subdominant tidal effects between Earth and Mars because they're so far away. So the tidal effects fall off more rapidly than 1 over r squared. Whereas Earth-Moon, you have to worry, the moon makes our tides. We have to worry about tidal effects all the time. So to back out a clean signature of a wobble and then reconstruct the path of the perturber, the Earth-Mars system is in that sense more clean. There are fewer confounding effects, gravitational or otherwise, that we'd have to worry about.
Wasn't there a recent high-energy stray neutrino?
There was, and that was another great fun example. So there are a couple of these. There's one very high energy one. The record holder so far was announced, I think, only in February of this year, recently. It had been detected roughly 2 years earlier, and the collaboration wrote up the paper recently. But there have been other ones of lower than that, but still really high energies found by things like the IceCube collaboration, which is in the South Pole. So IceCube has been operating for approximately 15 years. They've detected many, many neutrinos from outer space. For a small number of them so far, they've been able to identify a point-like astrophysical source, a so-called blazar, or there's something that went bang in the sky, and all kinds of stuff came out. High-energy electromagnetic radiation, neutrinos, and so on. And they could identify the path and timing. So far, of that set, there are about 6 high-energy neutrinos that IceCube has found that are so much higher energy than those, about 1 million GeV, so it's called a PeV, 10 to the 6 GeV and above, not one of which has so far been identified with any known astrophysical source, point-like or otherwise. And then the neutrino I think you have in mind, Curt, is about 100 times more energetic than that. So it was about 220 PeV, so 10 to the 8 GeV. And that was detected by a different collaboration, the KM3-NET collaboration, which operates an enormous neutrino detector within the Mediterranean Ocean. So large, cross-section. And so again, with a terrific PhD student, Alexandra Klipfel, she and I realized that again, if this hypothesis has any legs at all, that dark matter consists all or in part of primordial black holes, and again, critically, that the black holes form with some non-trivial mass distribution. Most come out with one mass, but there's a small subpopulation of smaller ones. Those smaller ones, some of them would survive to this day and be actively Hawking emitting. And our understanding, at least as of now, of Hawking emission is that it really is a runaway process, that the black hole takes a long time, emits hardly anything at all, gently loses mass, and then falls off a cliff. So that in the last fraction of a second of the black hole's lifetime, it'll be emitting all kinds of extraordinarily high energy particles, all the standard model degrees of freedom, and if there exist any beyond standard model degrees of freedom, at energies that in principle could approach the Planck scale. And then you can calculate the flux, how many particles per energy come out from one of these exploding black holes. And in fact, you get very few particles, if any, at the Planck scale because the black hole is so short-lived by that point. It's such a short lifetime, it's just the countable rates are few. But you'll get a countable number of particles coming out with energies on the order of 100 PeV. If a black hole is going through that last kind of death rattle of Hawking evaporation at some distance like 300 astronomical units away from us, doesn't have to be right next to us. So it can be a large volume which has some likelihood to have happened. And so what Alexandra and I show is that this is actually perfectly likely to have happened on the order of one time in the last 15 years since these detectors have been in operation. If we consider a volume of space as the order of 300 or so astronomical units away, that's larger than the solar system. And if this is a kind of straggler from the small mass tail of otherwise ordinary dark matter that consists of black holes, meaning this would be a black hole that formed in the early universe. Down that mass tail, it formed with a smaller mass than typical. It was further along its evaporation lifetime now. And you have a not unreasonable likelihood, putting in a realistic form for the mass distribution at formation, carefully evolving that forward with careful numerics, and then saying, here's the size of my box, 300 AU, what are the odds? And the odds are pretty good that you have about one of these very, very high energy events every 10 to 15 years, which is at least consistent with this, not proving that that's the origin of this neutrino, but at least it's showing a really, I think, lovely congruence. The pieces really fit. That's not proof that's the source, but there are not other, to my mind, very well understood sources that are competing with that explanation. There are lots of papers coming out on this. It's an incredibly intriguing event, this extremely high energy neutrino. And to my understanding, there is not as yet any, let's say, more straightforward astrophysical explanation that's been put forward. And maybe there will ultimately be one. We don't know. But again, it was at least a self-consistent to say, if we really think black holes are out there, and they're really all or most of dark matter, you're going to have some straggler rare events. Let's be open to those as well.
One in every 15 years that it hits Earth, or that it'll hit the detectors on Earth?
Good. We split the difference. That would hit a region on Earth that's larger than any given detector, but small, but one such that it wouldn't hit both detectors. One might say, well, why didn't IceCube also see it, right, or something, or see others ones from that explosion? So I think the surface area we took, I'd have to look up in the paper. It's a little bit bigger than just KM3net, but a tiny fraction of the surface of the Earth. So we didn't give ourselves the entire Earth as our target. We thought that would be, that wouldn't be realistic. So we wanted a cross-section where it's reasonable to hit that, like hit the Mediterranean, but not the South Pole. I mean, that kind of thing. Yeah.
So we've touched on a variety of topics just with primordial black holes. There's the standard model. There's what's beyond the standard model.
Right.
There's the Big Bang and cosmology.
Mm-hmm.
There's intersolar system physics, which I didn't even think about prior to this conversation.
Yeah.
There's various experimental apparatus and then experimental thinking. So to tie this all up, what are you looking forward to? What's next for you? And I would also like to get to advice for students who similarly want to tackle everything.
Let me start with the last one first. Don't tackle everything at once. I mean, boy, that's a recipe for frustration. So I don't know if it was sufficiently clear as I was narrating and rambling along. I've had such an amount of fun tackling these projects, not exactly one at a time, but one kind of flows to the other. And so that meant that I've been very lucky, extremely lucky, to be able to take the time, learn what I can on my own, critically learn with groups of colleagues and students, project by project, because each of these kind of requires and deserves just a lot of close focus. So I don't want it to, it's not like we're going to just do all at once. That's just a recipe for heartbreak and frustration. So partly it's be open to some really fun questions, but also recognize that each of these is going to deserve and require the really sitting still, really sitting with these and going through all the kind of emotional cycles of this is brilliant, it's terrible, it's brilliant, it's terrible, I did it, I lost it, all that kind of ride, day to day, week by week, month by month. It's not easy. If it were easy, it might not be, frankly, so fun. But the happier flip side of that is, we live in a really amazing universe that's complicated with lots of moving parts. And lots of people know a lot about aspects of that, including how we can learn more, like in instrumentation and experimentation, as well as theoretical techniques. And so none of us does this alone. None of us should try to do this alone. Not only is that lonely, it's just like, my own horizons have been so much broadly expanded by the opportunity to work with experts and students who are becoming experts, on a range of things. And I have to know enough to make sure I'm not fooling myself or my colleagues. I have to get up, do the work, steep learning curve, joy of learning new things, but I'm not doing it kind of on my own each time by any measure. Nor do I think would that be fun or intellectually satisfying. So with these entanglement experiments, the fact that Anton Zeilinger thought these would be interesting and fun, that's what made these possible. That's what made these feasible, right? The fact that, and it can play that game over and over again, each of the projects that we've talked about here. So for advice for students, I'd say, don't shy from really fun questions. And then get the help that you need. I bet to say team up with people who don't know those answers either, but probably have other tools that are already quite familiar to them that might be new to you, and you'll know things they don't know. And that, it sounds very kind of sweet and we should all join hands, but I just have really experienced that over and over again. That there's a way of putting things together.
The joyride is better with people in the car.
Yeah, that's right. Because I didn't know where I was going and they knew how to fix the spare or whatever the analogy would be. That's right.
So how do you find people to come into your car? You can't just drive by a gas station and then say, hey, hop in.
One way is to get a gig at a university. That's hard to beat that. So I'm immersed in a community of colleagues and scholars, from undergraduates through PhD students, postdocs, and fellow faculty across the institute, across MIT, and of course beyond. So partly there's something I think really magical, I really mean that, about the academic research community. And it's very precious, and it took a long time to build it to its current state. But one way is we have people coming who want to ask similar questions all the time. And that helps to get people in the car, so to speak. Another way, I think, is to, I don't know how to say it, if you can, kind of have fun with it, because that hopefully sets a tone to saying, let's take this drive together. The questions are meaningful. We'll all learn things we don't know now. They're probably going to be of interest to other people we don't even know yet. And so being open to collaboration and to asking questions that sound hard and interesting, right? And it's getting that balance can be tricky, but where you and other people are going to learn something. Maybe it doesn't pan out and you'll learn from that too, Maybe the effect goes away and that's cool. No one saw that coming, whatever it might be. What I'm interested in now, I think we touched on a few of them. One is really trying to learn more and dig in more on this kind of fundamental black hole physics, things like cosmic censorship, which is a hot topic. There are many experts who know tons about that. And I'm trying to, with Alba and some other colleagues, trying to say, what can we contribute to that? What questions were they maybe not focused on about things like, say, a black hole in a medium or dynamical space or other things that are on some of their minds, but what can we bring to that as well? And I'll learn a ton from that. I already have from even the effort so far. So one of those is, again, very kind of abstract, theoretical, mathematical. And I'm having a great time with it. And the other is going more like what we were talking about near the end. Instead of only relying on Mars being perturbed or not, what would it take really, is it feasible to build purpose-built, inexpensive satellites and put them where we want them?
Right.
So could we optimize their orbits so they're not only in the ecliptic? Could we instrument them not only so we can range them, but could they have little, inexpensive cosmic ray detectors? How would we do with that?
These CubeSats.
Right, like CubeSats and so on. That's right. What would it take to do a fleet of them? Could we use them to detect other exotic gravitational effects, like a gravitational time delay? If we really know the fleet of them and they have really disciplined clocks, could we do other beautiful gravitational tests that would be consistent with a black hole but not a typical asteroid? So suddenly it invites conversations with people who know a lot about things like CubeSats, about very fancy clocks, about ranging, about computer simulations. And again, I know very little about each of those, but I sure look forward to learning more. And it's in the service of what's the world made of and how might we know? And are these primordial black holes really here, or are they merely a very pretty idea? And maybe they're just that. We've already learned a lot from chasing the pretty idea, but wouldn't it be something if they're also part of our universe?
David, what drives you other than curiosity?
A couple things. Curiosity is a big one. Another one, it really is trying to build a space where younger folks can learn a lot of stuff and take those ideas and those skills where their imagination takes them. And I say I take the role of being in education really seriously. It's a great privilege and a responsibility. And again, that sounds very, I don't know, it sounds like it's on a Hallmark greeting card, but I really mean it. I mean, to be able to watch a younger person who has questions like I had when I was, a young person once back in the day, and watch them develop incredible skills, but also help them foster their own and maintain their own curiosity. What do they want to do with their skills? It doesn't have to be in academia. What do they want to do in the world? What do they want to do to do and make and build and learn in whatever setting that excites them? That's pretty amazing. And being surrounded by people from undergraduate through PhD, through postdoc, through excited and eager young junior faculty to really senior people. Let me share one last story. One of my very dear colleagues on this black hole journey is Ray Weiss, who's merely 93 years old, Nobel Prize winner, who helped dream up, design, build, and lead the LIGO project for decades that first successfully detected gravitational waves almost exactly 10 years ago. Ray is just a treasure. He's a treasure. He's incredibly humble and down to earth. And I have these meetings with a first-year undergraduate and Ray Weiss and sort of every stage in between. And if that's not a source of inspiration, to get me out of bed in the morning, I don't know what would be. So that's the kind of community of people who are still learning. Ray is still learning stuff and asking us questions, and we're learning from him too. So that's a pretty great gig, to be involved in that kind of journey together, to try to say, again, what's the world made of and how would we know?
Professor, thank you for spending so much time with me.
Curt, it was really a pleasure. Thanks so much for having me on. I appreciate it.
All right. That was fun.
I've received several messages, emails, and comments from professors saying that they recommend Theories of Everything to their students, and that's fantastic. If you're a professor or a lecturer and there's a particular standout episode that your students can benefit from, please do share. And as always, feel free to contact me. New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, "Hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts?" While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook, or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, Toll listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Jaimungal and donating with whatever you like. There's also PayPal, there's also crypto, There's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.